Okay, so let us start this class. So if you remember in the last class, calculated scattering amplitude came out to be I Z where for this line, this was the scattering amplitude and that is the electron is scattered with the classical electromagnetic potential that it sees into a positively charged nucleus. So this is electron momentum T in S. The electron once again is momentum T prime, speed is prime, and you have the UCL cube. Not writing this CL here anymore. Just remember that this is a static electromagnetic potential due to this positively charged nucleus. And in the last lecture, we had actually calculated scattering amplitude to be this, and then we just squared it up to calculate the probability of scattering this electron on this electromagnetic potential due to the nucleus. And from there we calculated the cross section, and the cross section actually reproduced the Rutherford scattering cross section formula. But whatever we did in the calculation, we assumed that once we derive this, then we assume that we are in the non-relativistic limit, and in the non-relativistic limit, things simplify a lot, and then from there we obtain the or derive the Rutherford scattering cross section formula. But what we shall do today is we shall look at relativistic scattering and try to take into account the relativistic correction to this uh, scattering cross section, to the scattering cross section. For that, what we need to do, we need to calculate this object. To calculate this. What are we doing here? We are basically seeing the spin of the electron. It has two possibilities. It can take two states. So what we are doing is we are summing over the final spin states, the states that it can take, and we are averaging over the initial spin states. Since there are two initial spin states, the average means that we have to sum over S and divide by a factor of 2, because there are two states, and we are summing over the final spin states S prime. We are not averaging over the final spin states. So it is just a sum over S prime. There is no division by a factor of 2. The factor of 2 comes only due to averaging over the initial spin states. And we need to, and what we want to calculate is this object. Okay? So we know what this is. This is basically equal to half summation S prime. This here we shall only look, because the other factors you can take into account later. See, this is a mod square of this quantity. So if you take a mod square of this, we will obviously have this factor. This will be squared up. So this I will go away. This will become z square e to the power of 4 divided by this whole to the power of 4. But we are, for the time being, we are not writing that factor. What we are doing is we are just looking at this factor, and we shall calculate this factor for the time being. So let us look at this one. quantity, then write it in the following way. Just straight away, let's first write this factor. Then you need to take the complex conjugate dagger. So this is what we require. And this factor, can write it. Then the QSP no 0 U bar SP gamma 0 S prime okay. You can actually show that the complex conjugate of this quantity is basically this. This is, you can say, from here to here. How to take a complex conjugate? So, to take the complex conjugate of this quantity, you will get this. I keep it as an exercise for you to show it. This is, you can say that this is the spinor trick 1. So this is a trick involving a spinor. Let me call it spinor trick 1. This is the first step. Now you can use second trick, the second spinor trick, which is the spin sum trick. So you can immediately see that before applying the spin sum trick, I shall do one more step just to write things in a nice matrix form. So what you can do is you can write this full quantity as S prime. Let me just see the indices that I have used so that it tallies with the calculation that I have done in my notebook. So this is Q bar S prime alpha prime. So I am saying that this index is alpha. I am just putting an index there. Then gamma 0 alpha beta. So this is alpha, or this is alpha beta. Therefore, this is Q is beta P. This is done. Then you have this one, Q bar S beta. So I'm putting index here, beta. This will be gamma naught. Just put this here. Okay. That will not change anything because we are using mostly negative signature. Okay. Dual component UF. So here 0 beta And the index that I used is lambda. And then this is straightforward. This is q s prime lambda. That is okay. So in this step, what I have done, please look at this step carefully. I have just written down the indices explicitly. And now, what we shall do is, we shall apply the C03 to, this is sum over S. So, if you carry out this sum, this is the spin sum formula. You can use the spin sum formula here, which is U bar involves this formula which involves U and U bar. At the same momentum P, same S and sum over S. So what the answer that you will get here is simple bar S alpha P prime gamma 0 alpha beta. Now you use the spin sum trick at this point, and this will give us P slash plus n beta. So you can see that one of the summation over S is gone now. Gamma naught beta is prime lambda. Now we can do another thing. You can, since these are all numbers, because I have taken the components, initially these were column vectors and matrices. But now see the advantage of writing this in this notation by writing of indices explicitly is now each of these are components of matrices, and therefore these are basically numbers. So you can put them anywhere you like. So what I shall do is I shall take this factor, put it here. If you put it over here, you can again apply the spin sum trick. Now you sum over S prime. So if you sum over S prime, this will give us. So now you see all the summations are gone. We will get gamma 0 alpha beta P slash plus n beta then gamma 0 beta lambda, and then u bar is there, sum over S prime, the indices are lambda. So this will give us u prime slash plus n lambda alpha. Okay. So the rule is u bar. So put the indices of u first and then beta. That is the one. Okay, lambda. Now look at this result. This is gamma 0, alpha beta, then this factor beta beta, then this factor beta lambda, then this factor lambda alpha. Therefore, this is nothing but half trace. Now you can get rid of all the indices. So trace of gamma naught slash n gamma naught and slash. Okay. So what we have obtained is, so this quantity that we wanted to calculate, we have first of all used the spin of trick 1 to write down the complex formula with this fashion in this way, and then we have applied the trick 2. So you can call this trick 2 twice to carry out the sums over S and S prime, and once you carry out the sums over S and S prime, what you get is a trace. Okay. So now everything calculating this object has boiled down to the calculation of a trace. So we need to calculate this trace. So let us see how can we calculate this trace. So we can write this as half trace gamma 0 dash gamma 0 q slash. So what we need to do is we just need to multiply everything. Straightforward multiplication. This is therefore equal to half trace of. So we need to multiply now. This will give us gamma 0 slash gamma 0 plus m gamma 0 square. But gamma 0 square, you know, it is identity. Okay? This is one of the properties of gamma matrices. And then we have this factor, this slash plus m, that is equal to half base gamma 0 slash gamma 0 slash. So this multiplied by this, then we have m slash, then we have this plus m gamma 0 slash gamma 0, then we have this square. Obviously, there is an identity over here, which you can write or you can omit. When I am writing n square, it actually implies that this is n square multiplied by some identity. Because once you put the this object, the indices thing in a trace form, now this is basically the trace of a matrix. So this is no longer a number, it's a trace of a matrix. Now you can see that you have this p prime slash actually means that this is basically gamma mu p prime mu. Okay? And so it basically means that this is a number and this is a matrix. So this trace of this gamma mu. Now we have to use the third trick, which is trace of odd number of gamma matrices is 0. So this term is 1. So this is trick 3, which is trace of odd number of gamma matrices. So this is also gone. Here also you can see that there is one, 2, and another gamma coming from P slash. So these are the product of 3 gamma matrices. And you have to take the trace of 3, the product of 3 gamma matrices. So this term is also there. Also gone. And now we have half trace of gamma 0 P slash. You can see that this term is not 0 because there are 4 gamma matrices here. So this is P slash, this slash, and trace of A plus B is trace of A plus trace of B. So you can apply, so you can write this term separately. So this is half trace of n square identity matrix, but then identity matrix is a 4 by 4 matrix. Trace of a 4 by 4 identity matrix is 4, and therefore this will give you a 4n square divided by 2, so it comes out to 2n square. Now there is no identity here because we have taken a trace here. This is twice n square. This is purely a number. It's not a matrix. So we have used the fact for the last term we have used trace of identity matrix 4. Is this clear to everyone?
Yes, sir.
Okay, good. So what we have now found is that we have obtained this quantity. So let me show you the full board now. So we have obtained this quantity to be equal to half trace of this object plus twice n square. So now we need to calculate the trace of the other part, the non-trivial part. And for that, what we need to do is use the following formula. We have to use this formula. This trace of gamma nu, gamma nu, gamma nu, gamma nu, gamma rho, gamma lambda. The formula for this is the following: it's 4 beta mu beta lambda minus beta mu rho and lambda plus beta mu lambda lambda. So we have to use this formula, and you can see that if you use this formula, then our aim is to calculate this thing, trace of gamma 0 p slash, then we have gamma 0 p prime slash. We need to calculate this, but this is basically trace of gamma 0, gamma mu, gamma 0, gamma mu. This is p mu, p prime mu. These are numbers, so you can take it outside. So we need to calculate. So this is a product of 4 gamma matrices, and therefore we need to use this formula. To use this formula, you can see that this will give us beta 0, beta 0 mu, the first term minus beta 0 0, beta mu, and plus beta 0 mu, beta 0. Thus, we have applied this formula straight away, and then times we have p mu and mu. Okay, so there is a p mu, p prime mu sitting outside. Now you can use the contraction of theta with these p mu's, these 4 vectors, and there is obviously at least a factor of 4. There will be a factor of 4. Good. So,
Can you zoom in kindly? Can you zoom in kindly?
Okay. Okay. Can you see now? So we are
Yes.
trying to calculate, and here we have just taken out these factors p mu and p prime mu, and then applied the formula for the trace. This is the formula. And now if you contract theta 0 mu, so this will give us what? This will give us p0 for the first term. For the second term, we have 2 times 0. This is the first term. And this theta 0 0 is 1. So we have minus theta mu contraction with p mu p prime mu. So this is basically p mu p prime mu. The second term. And the last term, this is once again. This will be once again p prime 0 and p 0, right? So you can just put in a factor of 2 because it adds up with the first factor. This is what we have. Okay. So this gives us 8 p 0 p prime 0 minus 4 p mu and mu. So we have computed the trace now. This is the trace formula for the trace. So let me again go to the other side of the board. The portion out, this portion out. So this trace of gamma 0 P slash gamma 0 P slash, this is basically equal to 8 0 0 minus 4 this is equal to 8 this will give us P0 0 minus P I. If you sum it, you get a minus if I take it upstairs. So this will give us P vector or minus. Therefore, this is nothing but this is 4 times 0 plus 4 times, so I can take the 4 common, P vector. Okay. So we have calculated the trace explicitly. Therefore, if we just add everything up, so this quantity that we have here is, therefore I can just remove this part.
Sir, I have one question.
Yes.
Sir, inside the trace, you are moving past P mu. Uh, uh, you are moving P mu after gamma 0 and gamma mu. How do you know that those two operators actually commute? I mean, gamma 0, gamma mu with
Right.
P mu.
Right. One.
Sir, mm, when you are calculating the trace gamma 0 P slash gamma 0 P slash prime,
Yes.
then you are taking P mu outside. I mean, P mu prime is at the at last, but you are taking P mu past gamma 0 and gamma nu. Do they?
P
They
mu
do
does
not.
not, there is no commutation relation between, see, P mu is just a number. With respect to the gammas don't have any commutation relation with P's. P slash
Yeah.
is basically gamma mu, P mu. Okay. And what are these gammas? These gammas are matrices. So you can actually sum it up. It is gamma 0, P0 plus gamma I, Pi. Right?
Yeah.
So you can actually, these P's are basically with respect to these matrices, these are like numbers. These are 4 vectors in the space time, in the flat space time.
Okay. Okay.
Okay, so
Here
there
they are
is
not
no
like that. Okay.
commutation relation. You can take it, you can put it anywhere you like. So ultimately, what we have is the following: half of summation is S prime U bar S prime when gamma 0 S mod square, that is equal to, this is equal to 4 P0 and P0 plus P vector prime vector plus Y0 square. This is what we have. Huh? Where will you after, where will you have a two? Half of this. Oh, okay. I am not. You need to say that I am not taking this factor. Okay. So maybe there is a division by two due to this factor. You are saying that we have not taken this factor. Are you sure? Let me just check.
That will be 4m square, I guess.
Just a minute. half. Okay, so this factor, this will be 2, right? Yes, yes. This ask. What is the question that you have?
No, now it's okay.
Now it's okay. Okay. I just forgot to divide this factor by 2 because this is a trace, but there is a half division by 2 here, so that is by 2. So now, I can basically combine this. Okay, you can take the 2 common. Now P0 P prime 0, this we can write it down as twice P. Okay. And this you can write it down as P square. So this is, since mod P is equal to mod P prime, because the scattering is elastic and the angle between them is positive. Okay. So this is what we have, and now you can write this as twice P prime plus square cos theta, and write it down as 1 minus twice sine square theta plus. Once again, EP and EP prime are equal. So I can change EP prime to EP. Because mod P is equal to mod P prime, therefore EP must be equal to EP prime. Therefore, this becomes a square. Square. And P vector square plus n square is again EP square, right? So you can write this as twice 2 of P square minus twice P vector square n square. So I've added P vector square plus n square is EP square. EP square plus EP square gives you 2 EP square. Okay. Now you can take this 2 common. This gives you a 4 EP square. 1 minus P vector square EP square. Okay. And we are almost there now. You can write this as 4 square 1 minus P vector square is 8 P vector square by square sin square by 2. This is P square. Where should I write now?
Sir,
Yes.
we are considering the relativistic case, so shouldn't there be an extra gamma square?
No, gamma will come. This is just
Yeah, sir.
momentum, right?
1 by root 1 minus b square
Come,
beta square.
will come. See, momentum, this is what? I just made a mistake. This is mv, so this will be m square v square. Right? T is mv. So that will give you n square v square. I'm using this. P is equal to mv. See, gamma is there. This is not the rate. Right.
Okay,
Just,
okay,
just.
okay.
Let's slide.
Sir,
Ah, yes,
we
please.
already used M as the rest mass. I mean, when we
Yes, okay, that is the thing. You are right. But M will actually get cancelled. I will tell you why. This M, let me write this M tilde.
okay, sir.
Okay.
Okay, sir.
Since we have the notation M for rest mass, that is the rest mass of the electron. But P vector is basically M tilde B. So here there is a gamma. Okay, this is not the rest mass. This is the relativistic mass you can see. Okay. And the energy EP, that is basically M tilde C square. E is equal to mc square, but m is, I have put it for rest mass, therefore I am using m tilde c square. Okay? So this actually gives us 4 e square 1 minus c. So this is m tilde square e vector square divided by EP square, that is m tilde square c to the power 4 sine square. Now you can see that m tilde has cancelled. Okay? So it
There
is
will
not
be no C, I guess.
there.
C will not be there because we have taken C equals to 1 already.
That is true, but if you restore C, you can restore C at the end of the calculation. You can do that. Just 1 second. Just 1 second. You are correct that there will be no C over here because C we have actually set it to be equal to 1. But if you want to restore C, then what will happen is you will have a C square here
Yes,
from dimensional considerations.
yes,
From here, because p vector square by p square, you are correct that the calculation has been done at with c is equal to 1. But now, if you want to restore c from dimensional consideration, see this is a momentum p vector square, and this is a ep square. This is sine square theta by 2, so this is dimensionless. This full thing must be dimensionless because you have a 1 here, which is dimensionless. It's a number. So this must be dimensionless. The only way it can be dimensionless is you have to put a c square here. So you can see now you can put in the factors of c square and everything after the at the end of the calculation from dimensional consideration. You have to put in the factor of c square here to get the dimensions right. And therefore, what you have is you have c square here. M tilde has cancelled away. C square by c to the power 4 cancels, so that gives you a c square. So now you have b square by c square, which is what? Which is beta square. Beta is mod b by c. So we therefore have 4 ep square 1 minus beta square sine square by t. So this is the full formula for the part that we are calculating, that we have aimed to calculate, and therefore can now write down the final formula. So what we have now is A1 mod square will be therefore equal to, we have to put in the factor that was already there in front, z square e to the power of 4 divided by 60 e vector 4 sine to the power of 4 theta by 2. This was already there, right? You remember from the earlier calculation that was there, and times the part that we have calculated now, the matrix element, the important part. This factor here that arises now is 4 e square 1 minus theta square sine square. This is the matrix element, the spinor part that we have now calculated. This part, and this is the factor that was there. You have to take a mod square, so you have this. So this 4 and this 16 cancels. Which number 4 downstairs. Therefore, the differential scattering cross section is sigma d omega. You have to just write this A1 square by a factor of 4 pi whole square. This will give us b square check. I've defined the alpha before. B square by 4 pi is alpha. This will give us z square. B square by 4 pi whole square is nothing but alpha square. This is the fine structure constant that I defined earlier. Divided by 4 4 sine 4 by 2. Multiplied by p square 1 minus s square sine square. Okay. And now what we can do is the following: p vector square. This p vector to the power 4. Are you clear up to this point of this result?
Yes, sir.
I think it is okay. Now you can once again see that you have the EP square. So EP square, you can make this p square and divide this by p square. So that gives you a p to the power 4.
Sir, I
But
have a
EP
one
square,
question.
yes.
Sir, that first part, I mean z square e to the power 4 by 4 into so 16
Uh,
p to the power 4, that is
uh,
for the non-relativistic part case,
No,
that
that is not
limit
the non-relativistic case. No, that is not the non-relativistic case. That is true for both the non-relativistic case. You look at your calculation, look at your notes. That is true for both, for everything. It is in general true. That is not true for any non-relativistic case or relativistic case.
Okay, sir,
The
I understood my mistake.
the
Yes.
relativistic case comes only when you manipulate, manipulate the spinorial part. In the spinorial part, if you take the spinors, if you take the non-relativistic limit, then you have a particular simplification involving the spinors, and that gives you the non-relativistic result. But
Sir, it
now
is
what you
clear.
have done is a truly relativistic calculation. This factor that you have in front has nothing to do with relativistic or case or non-relativistic case. This was already there, and this will be always be there. Now, p square by p vector square is what? That we have already calculated. Huh? 1 by 1 by beta square. This factor, you see, because this is m square, the m's will cancel here, that will cancel. Once again, so this factor will give you a 1 by beta square. 1 by beta square. So you can put in the factor of beta square here. So this gives you a factor of beta square.
That is c squared by beta square.
Huh?
That is c squared by beta square.
Anyway, now again you can forget about C. Let us forget about C. You can restore C appropriately. You can do that thing later. But if I put C is equal to 1, so now beta is basically just B. The C is equal to 1 in B, beta is just B. So the differential static cross section formula is z square alpha square by 4 b vector square beta square sine 4 theta by 2. This factor is 1 by beta square that I have taken into care here. That is beta square here. So this is no longer there. Times 1 minus beta square sine square theta by 2. This formula is actually the relativistic formula for the scattering cross section, differential scattering cross section. This is known as the Mott formula. This is Mott's formula. You know that Mott was a prominent theoretical quantum matter physicist, but he actually calculated relativistic correction to this Rutherford scattering problem, and he obtained this relativistic correction, this relativistic formula that we derived today here, and this was actually verified by doing the scattering experiments. This result was verified experimentally, and this formula is known as the Mott's formula for the scattering cross section, and it is actually a relativistic formula. So the takeaway lesson for today is what we have done is we have actually obtained the relativistic correction to the Rutherford scattering cross section, and we have done a fully relativistic calculation involving all taking into account all the spinors and applying the spinorial tricks that are there involving the spinors that we have applied. In the next class, we shall look into another scattering problem. This is a quantum scattering problem, and try to calculate the scattering amplitude in that case. So please go through the calculation once again at your home and see if you understand all the steps carefully. So you can see that this beta is basically the relativistic correction. If you take b to be very small, then this term drops out and everything becomes a which boils down to the standard formula that you have for Rutherford scattering. Okay, so is it okay for all of you? Just go through the steps.
Yes.
Huh.
In the previous class, while you calculated the first order amplitude,
Uh-huh.
there I see that you have neglected the normalization constants NP prime. Uh, why you have
So
done
no,
that?
normal. Actually, you are correct. You are correct. So what we have done there in that calculation is we have chosen a different normalization. We have chosen a different normalization. I discussed this matter with you in the earlier classes also.
Yeah.
So you can
Okay.
work with two different normalizations. I worked with a different normalization. Therefore, I did not write down the factors. I just worked with the spinorial part.
And sir, in you have expressed the a mu of x in the Fourier transform as a mu tilde of q,
Yes.
and the form of a mu tilde q you wrote it as z of
One,
mod of e by
one,
q square.
it is
Uh,
1 by q square.
how
Yes.
can you derive that form?
You derive it yourself. That is up to you. You have to derive it.
Okay.
You try to do it yourself. It is a very standard result. You know how to take Fourier transforms, so you should be able to do it.
Okay. Okay, sir. Okay.
Okay.
Yes, sir.
Okay. So let us stop here for today.